So let's say we have to split a particular feature. And when we split this feature, let's say we have like 3 positive class and 2 negative class. And here we have 6 positive class and 3 negative class, which means in total we have 9 features. And then the last split is called as leaf node, when the purity of the split becomes, let's say, 3 positive class and there are no negative class. Like there is only one category, which means the purity of the split is 100%. And this node will be called leaf node. Leaf node, right? So let's implement this in the formula. For example, the formula is again h of s equals minus p positive log base 2 positive minus p minus log 2 p minus. These minus are just a part of formula. These are positive classes and these are negative classes. Okay, so let's implement this. This p positive classes would be 3 by 5 minus of 3 by 5, because there are total 5 and the positive classes are 3. So the probability of the positive classes will be 3 by 5, and then log 2, and again 3 by 5 minus negative classes. How many negative classes? 2 negative classes. 2 by 5 log 2, again 2 by 5. That will give you a certain answer, let's say x. And this answer will give you will help you make the decision of how to split these classes. So let's say the split you got 50-50. There is 50% chance of positive class and there is 50% chance of negative class. This kind of split is the worst kind of split you could get, because so let's say we are predicting cancer, whether a person have cancer, yes or no. So when you have 50% 50 and 50 split, the algorithm is basically saying that yeah, there's 50% chance this person has, there's 50% chance he doesn't have. So there is no use of that prediction. Basically, we don't need that prediction. That is why 50-50 split is very useless is the worst kind of split in entropy. So, but to compute the best entropy, let's say you computed 2 entropies in the data set, but you have to decide which entropy is the best one and choose from those 2 entropies. How do you choose those entropies? For that purpose, information gain is used. Information gain is used. So let's talk about information gain for a second. The formula for information gain will be gain SA equals H of S minus sum of subset of the samples and by total samples. So this is not a complicated formula, but this formula is important to remember. This is basically the entropy that we calculated, and S is the total number of samples, and S is the the subset of samples which are considering in that particular case. So let's take the case again. We are splitting F1, we are splitting it in this way. And then let's say for this, from the entropy, we got 9 positive and 5 negative. And here we got 6 positive and 2 negative, 3, 3. So the split is done, right? Okay. So basically what happens is, let's say we have the entropy of h of s minus what is 8, the total we have to implement it in this formula. So let's say the total number of samples will be 14, 9 plus 5, 14. And the number of samples here is 8. That will be for first case, and for h of f2, which means here, it will be 6 because 3 and 3, sorry, here, by 14. And it goes on, h of f3. How many ever splits you have, you take those many cases and take the sum of all of those. This will give you some value, let's say 1. And you compare the two splits of the first split and the second split. Whichever split has highest y value, which means highest information gain value, that is the node you will be considering for your decision tree classifier. That is why calculating information gain is important. So we talked about entropy, we talked about information gain, and we should talk about Gini impurity. Basically, entropy and Gini impurity do the same work, but usually for bigger data sets, Gini impurity is usually preferred because of the simpler mode of calculation. So the formula for Gini impurity will be 1 minus the sum of squares of positive classes and negative classes. These are basically positive classes, negative classes. You're taking the squares of them and you add them both and subtract the whole by 1. This is the formula for Gini impurity. It is very important. We can write it as the sum of probabilities of the classes. This is the formula for Gini impurity. So basically, Gini impurity is used because addition and subtractions are much more easier to compute than logarithms, which we have seen in entropy formula. Okay, that's the main reason we use Gini impurity. I think that's it for now. We do have one more thing left to discuss. Decision tree usually results in problem of overfitting. Overfitting usually means low bias, high variance. right? Low bias high variance means the the accuracy of the training data set is usually very high, and the accuracy of the test data is very low. But the ideal case for any machine learning algorithm would be low bias and low variance, right? So I hope you remember what variance and bias is. Bias, in simple terms, bias is basically the error in the training data, error in training data, and variance is error in testing data. Okay, so the ideal case would be low bias and low variance, but decision tree usually results in low bias and high variance. So when we use random forest classifiers, this high variance will be converted into low variance because of how it is computed. If you want me to explain random forest classifiers as well, I will do it. Please let me know. Thank you.